He's visiting Mumbai, so I just invited him to give us a talk. A couple of talks actually to come.
Okay guys, so I've been working in the security industry since around 1996. It's been a huge amount of fun for me. So this talk is kind of various cool ideas and thoughts and things that have come about in the process. So I'm going to try and not make it overly technical, but just kind of trying to get a little bit of a feeling firstly, how much do people know about security? So let me ask a couple of questions which are a raise your hand kind of thing. How many people write code here?
Not me.
Okay. How many people write any code related to security stuff?
What is security and what is cryptography?
Okay. So I guess security is a bigger topic, which is how do you keep your computer secure, how do you keep your data secure, and there are a lot of different parts to it. Cryptography is a relatively narrow part of it, which is all the stuff around encryption, digital signatures, that kind of stuff. Now I'll go a little more into detail just in that area. And in my introduction, I have worked in a few of these areas, not necessarily all of them. Antivirus is part of security. Firewalls is part of security. I'm not covering those kinds of things, just because that would kind of be a much longer and bigger talk. So let me start to go. Okay, somebody's not happy. Oh, okay, that's fine. The left mouse button works. Okay, so quick agenda. I'm going to talk a little bit about myself. I'm going to talk about why security stuff becomes important, independent of whether you are a developer, a manager, all that stuff. Cover that when we get there. Who are Alice, Bob, Eve, Grace, and Mallory? These are very valuable names. Basic functions around cryptography, and I'll kind of talk a little bit about these, not going down into the details, because I'll explain why I won't go down into the details also, but I'll just kind of talk about them and then what you can use, how you can build on top of that stuff even when you're doing regular programming. Talk about some other functions, and maybe we'll skip over this if people's eyes start glazing over and you all start napping in the middle of my talk. Don't trust your own designs is another slide which I think people should have in any security presentation, and I'll cover a little bit of interesting stories and questions, and we can go on that stuff. So, I like to call myself as a barefoot cryptographer, and where this comes from is, guys have heard about barefoot doctors? No? Okay, so it's a very interesting concept. If I remember correctly, it came from China, where they would train people enough, right? Because the answer is, look, you want to provide medical support to villages in a whole bunch of remote places. You can't possibly train enough people, doctors to go live out there. So you train people enough so that they can diagnose basic problems, help with basic problems, understand when a problem is serious enough that you tell the person, go to the city, right? So I'm a barefoot cryptographer. I know how to do my basics with it.
But if you were talking in IETF and on the standards committee, you shouldn't categorize yourself as that.
So it's
because
kind of...
that itself, the credibility is the credibility that itself brings. You saw as your first entry points to get your product sold. So going back to your first talk.
It was a very interesting experience. I was mildly disappointed. Standards bodies are semi-political places, right? So the answer, part of the reason I actually did well out there is because I was writing code. And IETF is one of the few standards organizations where running code counts for a hell of a lot, right? Because I was writing code, I could figure out what was easy, what was hard, and I could make a convincing thing, which other people couldn't do. So
his point is that doesn't qualify you as a barefoot cryptographer.
Alright.
He's just being humble.
there's some
overly
amount of
modest.
that. No, there is some amount of that. There's some amount
But I
of
get your
reality
point.
also. There is some amount of reality in that. Right? If you went out and said, boss, now go define your own hashing function, I won't go there because there are these painfully smart guys who, I don't want to have long conversations with either because my eyes will glaze over when I talk to them. Right? So I think that is actually not overly humble. Anyways, I have worked on a lot of different areas of security. There have been applications of cryptography and kind of going out using this stuff to do interesting stuff. And I'll talk about some of them later on. Some stuff around websites and how do you make websites secure or how do you test them for common problems. Right? So we built a product to actually attack websites before they go into production so you could fix these problems before they actually went live. Or if your site was actually live, you still want to test it yourself rather than have other people find out problems with it and then actually break your systems. Right? Worked a little bit with SSL and a little bit around VPNs to allow people know what VPNs are and what SSL is. If anyone wants,
virtual private.
Yeah, virtual private network. So you just need a secure connection between two places. You have enough of the basic building blocks available that then you can go build this up relatively easily. Strong authentication. So somebody was talking about this whole two-factor authentication where you get an OTP across. That's one way of doing strong authentication. There are others. So just as another interesting factoid, right? In security, there are 3 factors of authentication. Right? Sometimes what people do is they say enter one password and enter a different, more secure password, and I consider this to be more secure. From a security theory point of view, that is a completely false statement because finally it is, now you know 2 passwords. No. Whether I know 1 password, I know 2 passwords, I know a shorter password, a longer password, does not theoretically change the security profile. Right? Yes, my password should be strong. Yes, they should have alphanumeric, capital, lowercase, semicolons and special characters. All of that stuff is true. But a password is finally a password has all the weaknesses of a password. So in security, there are 3 factors of security. What you know, which is something like a password. What you have, which is something like a key, access to a token, access to a mobile, something like that. Anyone wants to guess what the third is?
Who you are.
Right? So Aadhaar card uses this, the whole biometric concept. Right? Okay, so here, right, just a simple security function. What is the problem with the who you are? From a security perspective, biometrics is wonderful. So knowing who you are is great. That should be the best way of doing security. That should be enough. Why is that not a great answer?
The acceptance rate of the system recognition is still on the lower level.
Assume that you can solve that problem. Assume that you can solve that.
Hassle, sir. Hassle, sir. Hassle. It's a hassle.
Hassle is always a legitimate argument, but it's an argument for against all security generally. But yes, that is a legitimate point. But no, there is another very, very, very basic problem. If a bad guy ever captures your biometrics, how do you change it? Right? So, I use my thumbprint Aadhaar. You got my thumbprint for some other purpose. Can you be me? Right? So, the weakness of biometrics is there is no great way of fixing it once somebody captures it. Anyway, so there's that. And then, of course, part of what I was doing was I also was kind of doing a little bit of Kidagiri where in school we had some Sun workstations. I don't know how many people over here remember Sun workstations, but
Solaris.
Suns. Well, no, this is before Solaris. SunOS. SunOS, long before Solaris, right? We are ancient. So we had Solaris workstations. You had a login screen. And I was kind of wondering how hard would it be for me to put my own login screen. Then I walk away from the computer with my login screen over there, let somebody type or username password, and then say, oh, wrong password, sorry, go away. It actually worked. And this was, it isn't a very deep thing to do, but this was kind of a little bit of Anyway, so why is security important? As a user, right? Whether you use your online banking, whether you use your credit card, your debit card, wherever you are using anything that is online available at will. As soon as stuff starts happening on the internet, this is something that you want to start being a little bit aware of, right? The website that you're going to, is your connection to that website protected or not? Can somebody eavesdrop on your communication, right? Till relatively recently, on a lot of websites, you enter your username password on a site that wasn't protected by SSL. What are the problems with that? So the problem with that is if anyone else is sitting between me and the website, the guy can see exactly what communication is going back and forth. The guy knows my password. Often I use that same damn password in 7 other places. They're likely to be able to get into my bank account without damage. So, as a user, understanding the basics of this, understanding what's likely to work, not likely to work is useful. Right? As a developer, if you want to do a good job in your engineering, you don't want to be introducing security code. A lot of security problems happen because developers haven't been trained. They're trying to do things really quickly. They aren't thinking about security problems, right? You're doing everything around, is the functionality working or not working? And that works to a certain extent. Then, if you aren't thinking about security problems, if you don't have a slightly teda dimag, you are going to introduce security problems, right? So having a little bit of that tedaness in your head is worth a lot, right? Which I think Indians generally have it in reasonable amounts, which is partly what I think has helped me in the field, right? Interestingly, I talked about this a little bit. It makes a set of programming jobs easier, and I'll talk about this. It's a specific kind of property when I talk about secure hash functions. So it gets a little bit more technical than some of you might want, but that's fine. And I guess as a manager, if you're managing software developers, you're managing projects, this is something that you need to keep in mind, because poor security can break a company completely, right? So if you are not worrying about it, you don't have people who are worrying about it, or you don't know how this is going to be dealt with, you are going to face a problem at some time. Right? It doesn't matter where you are, what company you are, because people are going to have access to stuff. Right? Again, to give you guys a little bit of a story, people use LinkedIn over here. N-1? Okay. So LinkedIn is a site for you to network with other people professionally. Big company had at least 100 million users. They were storing their passwords, they were encrypting the password without a salt. And I'll explain a little. Actually, do you have a whiteboard?
Yes.
Yeah, this is a whiteboard. Okay, so I'll explain salting.
Is there a duster?
So now I'm going to get a little bit into the weeds, and I'm going to cover, let me get to the LinkedIn story when I talk about salting, which I will do in just a few minutes, okay? But they were doing something that from a security perspective is utterly dumb. And they did it. And they were a company with 100 million users. They got hacked. Their passwords leaked. They had to go out and send out a mail to all the users saying, guys, we screwed up royally. Right? Now, the egg that you get on your face with a thing like that, and the CEO of the company at that stage is going to get awfully upset with whoever was responsible for this thing. Right? And there have been enough security break-ins that get reported all the time. So the answer is, look, at least make sure that you are doing hygienically the right things. It still means, I guarantee you, that your site can be hacked. Okay? But at least you have done enough to raise the bar that the attacker says, boss, this is a little bit hard, I'll go somewhere else. Right? But if the Chinese government is after you, move. Right? Now, unless you are working for the Indian Department of Defense and you've got the appropriate level of stuff, just say, boss, it's okay. Okay, so Alice, Bob and Eve, there are two interesting lessons to learn around this, right? So if you start reading any book on cryptography, they will start talking about Alice sending a message to Bob, Eve being an eavesdropper who can see the communication that's going on. I just talked about SSL. Eve is the eavesdropper. Grace is the government agent who potentially has a subpoena, who wants access to a certain amount of information, which is a big deal in the US these days. Mallory is the malicious attacker who can go out and create false messages and bad messages, and can these fool your system, right? Or for example, the difference between an Eve and a Mallory is Eve can see what's going across the board, but if, for example, I am paying you $50, if I can put that 3 times on the wire, suddenly you get $150, but that wasn't my intent. That's the kind of stuff that a Mallory can do. Now, the cool thing, at least the first time that I read about this, what I really loved about this is the names. Firstly, they started with A, B, C, D, E. For me, if two things start with the same letter, I mentally read only the first letter, right? And I think, interestingly, a lot of other people have the same weakness. These guys all start with different letters. They all tend to play the same role. Whoever is writing a security paper on whatever topic or similar roles. And if you look this up, you'll find a Wikipedia page on this where they describe the roles of each of these guys. There are a lot more. There is a C, there's a D, there's a, right? But they all play the same role, and it's a great way to tell the story, and it's a great way for a group of people now to start telling a story that other people can understand more easily. So I know these names are absolutely wonderful, but again, Alice is kind of a relatively good person sending a message to Bob. Sometimes Bob can have a malicious purpose to say that, hey, Alice sent me this message, Alice might want to say, no, I didn't. So sometimes Bob can do semi-bad things, but generally Bob isn't doing bad things. Eve is the person who's the eavesdropper. Grace, I thought this was really, really, really brilliant. Whoever came up with this the first time was a really good. Right? Okay, now I'm getting a little bit into the details, but I will try to keep this sufficiently high level. So as you can see, there is zero mathematics on any of these things. I have not used any functional notation or anything else. What are hash functions? So hash functions take arbitrary length strings and they map them onto fixed length outputs. Okay, fair enough. One way of doing it is I can take every string, I can map it onto the number 4, at which stage I have a hashing function which does things, might not be a very useful thing, right? Because now what am I going to use it for? But net, they take arbitrary length strings and they map it onto fixed length strings, and we can talk about specific hash functions. The properties from the hash of the message. Okay. So if there is a message M and it maps to a hash H, from the hash value, I cannot go back to the original message. Okay. So I do not have any clue what the original message was from the hash value. But from the message, I can get to the hash very easily and very quickly. Okay. So that's property number 1. Number 2 is I can't create a new message given a hash. So if I have M1 mapping to a hash, I cannot create a M2 mapping to the same hash. Okay, this is another property of hash functions, and we'll talk about the utility of this in a couple of slides. Or at least one utility. There are lots of utilities. 2 is number 3 is the probability of two random messages having the same hash has got to be awfully low, right? So one way of doing hashing, for example, is I could add up each of the character values. That's one way of doing a hash function. But now if I took a string and I inverted it, it would map to the same hash value. Or if I flipped 2 letters, it would map to the same hash value. You don't want that kind of stuff to happen, right? So probabilities of collision are very hard to make happen. I mean, two things. One is you can't make them happen. The other is, if I just pick 1,000 different messages, the probability of a hash is still going to be very low. Or I picked 1,000,000 different messages, the probability of a hash. If I change one bit in the input, half the bits in the output are likely to change. Not guaranteed, likely. Right? So there's some distribution probability, and now you'll have the mathematical gods come in and tell you exactly what that is going to be. But generally, one bit change in the input is going to change half the bits in the output. Okay, guys, familiar with bits and bytes, right? I'm not going. If I'm glossing over stuff, I can go more into stories too. That's fine too. The interesting thing now, this is an interesting programming exercise. So if I have strings and I want to put them into a hash table, right? One easy way of doing it is I do a secure hashing. I take one of the secure hashing functions and I can say, okay, I want to map it to a hash of just 8 bits. I can just take any byte from my hash and that's going to be a good hashing function, right? So now from a pure programming perspective, this becomes a very valuable way of going out and solving interesting programming tasks that have nothing to do with security, right? I think this is going to be the only example that I can come up with where security helps just general programming problems. But okay, going to symmetric encryption. By the way, I have picked these 3 areas very particularly. One was hashing, the other is going to be symmetric encryption, third is going to be public key cryptography. And these 3 often are the basic building blocks for a lot of other interesting stuff in cryptography, and I'll talk about that a little bit later. Right? I'll talk about Bitcoin if people have heard about Bitcoin. I'll talk about some other interesting things.
So you want to touch on that salt for LinkedIn?
I want to touch on the salt for LinkedIn, and that is going to happen. That is going to happen. Actually, it should happen in the hashing.
Yeah.
But I thought I had made a point of it somewhere. Going back is like this. There's back. Okay. So the interesting thing, I guess, is okay. One of the ways in which you can stop passwords, and this is where LinkedIn had messed up, is they were taking passwords and they were just hashing them and saving them in a password file. So now the deal is, effectively, if I have user1 as a password 1, his password maps to h1. If I have password 2, his thing maps to h2, right? But often what happens is, okay, so now the deal is, this whole file was saved somewhere, a hacker got it, he compromised it, he got to this file. Now interesting things happen. As a hacker, I can go look at a dictionary, I can take every word in the dictionary, I can hash that word, right? And I can create hashes of those words. Now, if I can figure out your hash is the following, I know which word it corresponds to, I've got your password. Right?
Dictionary meaning the normal English dictionary?
A normal English dictionary, I can combine it with a few other interesting rules. I can capitalize the first letter, or I can add a number 1 after it. I can put an exclamation. Hackers have figured out common passwords for partly through, listening to traffic that was happening on the internet and, various other ways.
But
so
what if my password
is a really strong password?
And it's not a word, it's not a context.
Sure. So they won't crack your account. From LinkedIn's perspective, 80% of the accounts are cracked, right? The 20% who use secure, or the 10% who use secure passwords, were big deal, right? But this was a huge deal, right? So now the point is, okay, so I've kind of already mentioned it, so people who know what salting is, please don't say anything. For people who don't know what salting is, how would you try and solve this issue? So, there are passwords. From a password, you want an easy way to figure out whether that was the right password or not, right? So, the server, given the password, should be able to figure out the right answer. But you never want them to map to the same thing. At this stage, you guys technically have all the information that you need to figure out this whole salting story. And obviously some really smart guy once upon a time figured this out many years ago, and I don't know who the guy was. But Unix used it, I'm assuming sometime in the 70s or whatever. So anybody wants to hazard a guess who does not already know what salting is, about how people solve this? Who knows what salting is? Okay, so other than the two of you,
I think I know.
okay. Anyone else wants to hazard a guess?
But you can use maybe system time and location to make it unique every time.
No, because the user enters his password once the first time around, right? But then you're verifying the password every other time. So how do you figure out the unique system time?
You're saying look up a dictionary, backwards calculate the password. When you're creating this hash, you add something to your password.
Then when the user provides me with the password, how do I get to that hash? Because the system has to verify that Girish logged in a certain time.
This other part that is being added is like the system time or something like that.
Excellent.
And you know the system time has changed the next time, so that time you use a different system time to
Okay, beautiful. That actually is the solution with a mild delta. Instead of system time, you use random number. Just use a random number generator, right? So then what people do is they take the password and they hash the password plus a random number. And what you do is you save both the random number and the hash. The hash that got generated, okay, so if this results in a hash h, what you are saving in your system is the random number comma h. So now when this user comes in the next time, he says, I am Girish, I go look up his random number, I do the hashing function, and if the hash matches, then I'm in business. Exactly your system time solution. Right? But instead of using time, they use time. And interestingly, I think the size of this seed has also started growing because people have now started getting bigger computers, so the seed size has to grow. So 4 bytes is no longer enough. Make sense? Was it clear?
Wherever the file is stored, the random number is also stored there. And the hacker gets that also.
He gets that, but now what happens is I can't do a dictionary attack that easily. I have to do it for each individual account holder. So now I have to go through all those words for every person. If there are dramatically weak passwords, I will still crack them, but it's much more work for me. Right? So yeah, this is kind of basic hygiene. The answer is protect this file. Don't let it go randomly, but trust that some employee can be bribed to go make that file available. Right? And so then you come into processes and stuff, right? Now, so security will involve who has access to that file, when do they have access to that file, can I track who ever touched that file, right? If you touch the file, then maybe I can do something interesting. By the way, this is kind of, in my head at least, this is kind of a cool, interesting stuff. So if this is not cool, interesting stuff, again, give me feedback and I can go down a slightly different direction. But whoever came up with this idea was a smart kid, like Girish. Okay, so I talked about that. Yeah, I think I finished this. Okay, so let's go to symmetric encryption. So symmetric encryption is actually possibly one of the oldest things that people ever did in the area of cryptography, right? And essentially the goal is, if you want to get a message to me and both of us agree that we're going to use a particular secret, can you get that to me through a courier who is not necessarily trusted? So courier should know the message. Even if the courier is tortured on the way, the bad guy cannot get to the message, right? And I don't know how true this is or false it is. There's something called Caesar cipher, which possibly was used by Julius Caesar, but look up the Wikipedia page to see whether that's true or not. But the story itself is good, so it's a perfectly good story to go with. So Caesar cipher, effectively you and I agree that we will do an offsetting thing. So what we will do is we will take every letter, we will add say 12 to it. So A will map to I think M, either whatever, right?
N.
A will map to L, thank you. There is the Caesar cipher, this, right? And so B will map to M, da 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 da, right? So this was kind of the first ciphering thing that was used a long time ago. That time was a pretty smart technique. Anybody wants to kind of figure out what are the downsides of it, and if you know Caesar cipher, then you don't answer. But for people who don't know the answer, what's the problem with this? What are the various problems?
Language.
Huh?
Language itself.
Language is a huge problem. Language contains huge numbers of hints. What are the kinds of hints that people get from the language?
Usually used words like the, or repeated letters like E. You can figure out the frequency.
Yes. Statistical distribution of letters, distribution of words if spaces are retained, all of those things start becoming issues. Caesar cipher, by today's techniques, terrible idea. Once upon a time, maybe it was a pretty smart idea. There are dictionary attacks. So now, even with new technologies, right? So DES was something that was introduced, if I remember correctly, in the 1960s, right? IBM, I think it was 60s, maybe 50s, 60s, whatever. So DES was introduced, but DES has a set of modes. Now I'm kind of going a little bit into the weeds, let's ignore that. Part of what you want to do is to make sure that when you are doing symmetric encryption, the same string does not always map to the same message does not map to the same output, because if that happens, then I can create a lot of commonly created messages, see what they map to, and then look for those patterns in an encrypted block, and then say, boss, now I know what's going on. So what people do is they effectively again use that same concept of the seed. Yeah, they put a random number. In this particular world, it is called an initialization vector. Don't ask me why. Maybe things happen at different times. But exact same concept. I put a random number in the front. I include that with the actual output, so the decryptor can also figure it out. And the other thing that you end up doing is you chain all this stuff together. So even if a latter part of the message is the same, it will still map to something different, because that whole sequence is going to be, the latter part of the message depends on what came earlier, right? So that's often used in, or nearly always used in any symmetric encryption algorithm. And these tend to be blazingly fast, even for large amounts of data, right? So these can happen nearly as fast as encryption can happen, as fast as you can actually transmit data. So the cost of doing symmetric encryption is close to zero. Okay? And again, guys, if this stuff is not deeply interesting, let me know and I can go in different directions. There are stories at the end, which are purely stories. Okay, public key cryptography was an absolutely amazingly brilliant invention, right? Originally created by Diffie-Hellman. Marty Hellman and Winfield Diffie, right? And independently created by somebody called Ralph Merkle. They came up with this idea. So the problem with the symmetric key encryption, which if I can go, get this back. Sorry. So the problem with the symmetric encryption is you and I have to share a secret, right? And you don't want to share a key. Key is sometimes called a secret, right? That's why, symmetric encryption, the other thing is called shared key encryption, other thing. But we have to share a key. And now if we decide we don't want to use the same key again and again, so we have a code book that you and I share. But if this code book falls into somebody else's hands, then they can start decrypting all of our messages, right? So that is also bad news. In fact, I think Washington got the code book that the British were using for their encryption, and that is why I was able to crack some of the messages during the American Revolution, which actually told him where the British were going to land up in a set of places, which actually allowed him to take particular actions and withdraw his troops from places and things like that. So it actually affected the outcome of the American Revolution. Okay, so the brilliant key, and why does public key cryptography help? There is a public key, there is a private key. Public key you expose to the whole world. It doesn't matter who knows my public key. You can send a message to me encrypted with my public key. I am the only person who can decrypt it. Somebody who does not have my public key has no access to those things. Now I can interestingly kind of, generate my public key on my own machine, and now nobody else, no government, nobody has access to anything that got encrypted form. Okay? What was brilliant about this idea was when he had symmetric encryption, even the original thought that such a thing is possible, I thought whoever came up with it was an incredibly smart guy, right? Falls into the domain of being a god, right? And then to actually come up with a technique to go do it. The big problem that it solves obviously is this whole key distribution problem. So effectively now my public key can get printed out in a dictionary, or the way people have also dealt with it is my public key is signed by a public key of an authority whose public key is well known, and this is how digital certificates work. So people familiar with digital certificates? How familiar?
So in audit and all they take digital signatures, no?
No, digital signature is a different thing, and actually we'll get to that.
HTTPS.
HTTPS uses digital signatures. When you connect to Amazon, you're using digital signatures, right? So digital certificates. All a digital certificate is really the site www.amazon.com. Public key is 579863, whatever, right? A big long number with a date, start date, end date. Essentially, this, and then there's some, and then there is something called a signature on it, saying VeriSign asserts this. Now, given that there was a standards body that created it, they put in enough other crap to make sure that normal human beings couldn't understand it, and they had job security for the rest of their lives. But this is essentially it, right? So now people only need to know VeriSign's. So the other thing that I have not talked about, which is kind of one of my other questions I was trying to get to at the end, which is the other brilliant thing that this is introduced, which is the concept of, as you said, digital signatures. If you know my public key, you can verify that I signed a document, but nobody else could have signed the document who didn't have my private key. And this is exactly what's happening out here. VeriSign is signing something, a document, saying that Amazon's public key is the following, and nobody can forge this particular signature. And Amazon can send it off to somebody else, and that guy knows that this is Amazon's digital certificate, right? The company I was at, Valisar, was, once you have issued this thing, suppose Amazon's key got compromised, how do you verify that it is still good or not compromised? That was our business. Slightly unrelated. Okay?
So you were a CA.
We were not a CA. We were actually a VA, a validation authority, as opposed to a certification authority. And it was hard marketing work to get people to distinguish between the two. In the credit card world, which is an interesting world, the bank that issues your credit card is not necessarily the person who validates it. Often there is a third party who validates it for your bank. Right? So there, in the US, there are companies like First Data whose only job is providing this validation business. Okay. Problems that solve. Okay. I'll get to that. So I already addressed this last thing, which is the other class of applications, which was digital signatures, which was not something that was possible till somebody figured this out. Right? There was no way of doing digital signatures in the digital world at all till that time. So that was kind of amazing. Now practically, as it turns out, public key cryptography, pretty much all the algorithms tend to be slow and they tend to be able to sign only small amounts of data. Okay? So, here is a practical problem. We do emails. I don't know if you people have used S-MIME, but S-MIME is the standard that is embedded in pretty much all the mail agents and now even in all browsers and stuff like that. Google supports it, etc., etc., etc. How would you do encryption of email? Because emails are large amounts of data, right? I can have an email that's worth 1 megabyte. If I want to encrypt a file of 1 megabyte to you, I have public key cryptography. I know what your public key is. How would I try and encrypt it for you? And I've given you this problem. One mechanism is I can kind of take, at one time, public key cryptography, with public key you can kind of encrypt, say, 1,000 bits of data, right? 1,000 bits of data is 128 bytes or something. But I've got a megabyte large file. If I tried to kind of encrypt every bit of it, I would kind of exhaust myself. So, how do you guys think people do that? Emails are encrypted, email encryption is quite possible. Bulk encryption, you do disk encryption or file encryption, all these things happen, right? And some of them can happen even with public keys. How would you do that? Anyone wants to hazard a guess? It's a cool problem, yeah.
Small blocks and then chain the cipher to the next block. Do it in smaller
You're
chunks.
partly there.
And then chain the next cipher with the previous block.
No, but with what? Public key?
Yeah, you can use the public key.
But then you have to do public key operations how many times? No? That's too expensive. That's too expensive. So,
To compute intensively.
to compute it. Yes.
Can we encrypt the whole thing using the common key and then encrypt that using public key?
Exactly. That is exactly what people do. So you go out and you generate a random number, right? You use this to encrypt the whole file, and then in the header of the file, you do a encryption just of this using public key cryptography, right? Works beautifully. That's exactly what email does. That's what disk encryption does. That's what everything else does. Okay, so that again, the first time that you figure some of these things out, I think it's just a lot of fun. Okay. Eraser. Other functions. Okay. This.
We don't understand some of the words on your slide.
Yes. You're not meant to. You're not meant to. So, HMAC is an interesting way of essentially verifying that nobody could corrupt a message. It's called a hashed MAC. So there are actually 2 points and 2 reasons why I put this up. Right? My next slide is going to be don't go invent your own crypto algorithms, right? And the deal is, at a conceptual level, what an HMAC does is, if Alice is sending a message to Bob, right? And
Can you write on the white part?
on this part is probably understood. Is this better? Yeah. Okay. Alice is sending a message M to Bob, and we are afraid that somebody might go in and mess with the message, right? So we aren't necessarily worried about the data being encrypted or not being encrypted. We're just worried that somebody might change 2 bytes in the message or change something in the message. Bob wants to verify that this message is accurate. So, one way of doing it is you send the message and then you create a signature on the message and then you say, here's the signed message, go read it, right? The other thing that you can do is if Alice and Bob have some way of having a shared secret before them, right? Then what Alice can do is Alice can send across the message and the HMAC of the message to B, right? And B knows that only somebody who held that secret could generate the HMAC.
So write a dash over 3 dash.
No, so there's a key out here. So there's a key. So the way you're doing HMAC, so you're sending across the message. In addition, you're sending across a small number of bytes, only the size of a hash, along with the message. And the hash is with a key that these two guys know, and the message itself.
The key isn't clear?
No, you're not sending across the key. You guys have exchanged that key, right? So, but the deal is that this kind of is not a lot of data to send across. It's relatively cheap to compute, it's very cheap to compute, and it's very cheap to send across. Now, by default, I would say, hey, we talked about the hashing functions. So I take any hash function, I add a key and the message, I concatenate those two together, and that's a good way of doing an HMAC. That's how I would have designed it. And then of course you have these crypto gods who kind of come in and say, no, that is weak. And then they prove that it is weak, and they prove that there are 7 ways of attacking it. So in general, the algorithm's a little bit deeper, and then they mathematically prove why an HMAC needs to be something where you are doing the hash of approximately the key, the message, and then they do something else with the key at the back too. Right? So they did this, and this kind of prevented a set of attacks. And I haven't ever got, as I said, right? I learn enough crypto that I need to know, and then I trust the gods to go do their homework for me. There are mathematical proofs that I will go glaze over when going over them, so I don't claim to understand it, but that's kind of what, and HMAC itself is a little bit more involved in this, but this is good enough for our purposes. Makes sense, but this is kind of partly why don't define your own functions, because the gods will come and beat you. Right? Okay, so password storage and salts, we already talked about that. I guess SSL you guys are already familiar with, so I won't spend a whole lot. I'll just give you guys an interesting story, and I think I was talking to you about it. The kinds of attacks that people devise on SSL. So SSL was a well-defined algorithm. Lots of security experts had looked at it, and they figured out that this is a good secure algorithm. There's this smart guy who came up with this mechanism. Okay, maybe I need to explain a little bit about SSL. Well, okay, so I'll abstract it even a little bit more. What happens when you're doing SSL? We talked about digital certificates a little bit, right? So what's happening is at some stage you are sending some data encrypted with the recipient's public key or the server's public key, saying decrypt this, then you can decrypt the rest of it, right? That happens initially in a handshake stage. What this guy was doing is he was sending across messages and figuring out how long the server took to respond or to acknowledge that message. Based on the timing of that, the guy started, and sending across 1 million messages or 1 billion, he was able to figure out the key on the server without having any other access to the server. So this was called the timing attack on SSL. The way around it is people do something called blinding. So what you do is you kind of take the key, you take the complement of the key, and you do an operation with the key, you do an operation with the complement of the key. That way the amount of time taken is approximately the same, irrespective of how many ones and zeros there are in the key. And that was the mechanism that was used to solve the blinding attack. And then of course the same guy, very smartly, awfully smartly, figured out something to do power analysis. Exact same, similar technique. to kind of figure out the part that is being used by a smart card chip to figure out the key on the chip. And he used this to make millions and millions and millions of dollars because every smart card vendor had to then buy the techniques because he patented those particular techniques. So in my earlier talk, I did not talk about patents at all, and generally I think patents are not a very useful idea in the software world. This is one of those cases that completely disproves that statement. Patents were worth their weight in gold. Right? Fair enough? Okay, nonsense I think is too much of a level of detail. Initialization vectors, we already talked about sorting and initialization vectors, same thing. Okay, next slide. Don't trust your own designs, already talked about that. Lots of people like to come up with new algorithms and new techniques. In general, the security community will tend to ignore all of these completely. So unless you can get a god, a security god to come in and say, yeah, this looks like a good technique, most people will say, that's wonderful, but I don't have any time to spend any time on this because every Tom, Dick and Harry who has gone through a first crypto class wants to come up with their own algorithms, right? So unless you get a god, but the more interesting thing is, even if you get a bunch of gods to say we believe that this is secure, the industry in general is going to guarantee take 10 to 15 years because over time people figure out more and interesting and different ways of attacking stuff. So they take 10 to 15 years before they will even consider the algorithm seriously. New algorithms are painfully complicated. And no startup should be in that business. In general, it's not clear that there is any money in that business. There might be some bragging rights which are worth something, but not clear that there is any money in that business. So, don't go in the business of inventing your own things. Do use the basic mechanisms to say, okay, based on this I can, or see if somebody else is doing something as close to identical as what you want. Try and see if you can adopt that, but even then try and get somebody else to take a look at it, who has a little bit more of a paranoid personality.
Is that a real theory, the snake oil?
Snake oil is not a theory, but it's kind of a commonly used term in security that, this guy's a snake oil vendor, and you'd be surprised at how many startups have got funded with this brand new beautiful security technique that solves all problems in sliced bread. And they really can't go, right? And even in cases where the technique itself is good, people are just reluctant to adopt it because the good standard certified open source mechanisms, why do I want to go after something that is so unlooked at, right? And who knows who paid you to do this, right? If tomorrow the Chinese government paid you to kind of publish this algorithm, you are a front for them, who's going to do that? Don't come.
So is Tor a front for the government?
Tor was built originally by the US Navy as a way of protecting communication. It is not necessarily a front, but the answer is that if the NSA is after you, they will be able to figure out your communication. Do not trust that Tor will protect you from the NSA, from a random Joe Schmo. And I don't even know if it will protect you from the RIAA, for example, or that industry, right? It might not protect you from that world either.
But how could NSA tap into Tor?
So they won't necessarily tap into Tor, but they start using statistical techniques to say that I saw these many bytes come in here, I saw these many bytes go out there. And they're kind of going out and saying, okay, this is happening with some frequency, these two are likely to be connected.
What if I change my Tor circuit every time? Or
How often will you change it? And how much of a chance do you want to take? And how much data do they need to reach statistical significance? So now you are starting to tread into an area where you are asking for a certain amount of ping. right? And NSA has awfully smart people. You know, there was a time, maybe before Snowden, where I said, ki boss, NSA used to be really smart. If you guys know about the DES algorithm, when DES came out, these guys inserted certain keys in there, right, into something called S boxes of DES, which allowed them to break into it, which nobody else knew how to break into. 10 years later, the smartest cryptographers were finally able to go figure out these weaknesses and said DES is weak. But for 10 years, NSA had full access to the stuff, right? So after that, I was certain, ki boss, you know, by the time I was at Vallis also, this was in 2000 or so, ki boss, NSA maybe was smarter than everyone else that time. Now they're no longer that much smarter because all the smartest software engineers will want to come and work in the industry because you earn so much more. And then you have people like Snowden come out. At that stage you say, boss, don't go there.
So since you're referring to Snowden, what exactly did he do? Was he clever? Was he hardworking? Was he at the right time at the right place?
Actually, Snowden in some sense was not necessary. I mean, he was clever, but what he did is he downloaded a whole bunch of stuff that he had access to that people shouldn't have given him access to. He was a contractor for the US government. Why the US government should be giving a contractor access to all these secret plans if he's not deeply involved in them is kind of the world in
So
general.
he already had data.
The data existed. The data should have been only accessible to a very small set of people. You can trust incompetence in general. Happily for us, the world is a semi-incompetent place, right? Which is why Snowden was able to download this. Obviously, Snowden got around any kind of controls that the NSA had, or that these guys had in whatever agency he was working at, to potentially detect this kind of stuff. He was able to get this data out without triggering any of the alarms that people would have had. You can go out and say, look, why is this guy going out to a secure site so often? Why is he uploading so much data?
But all the data he got wasn't clear. He didn't have to manipulate that data and decode
No. He had access to that data, right, which he shouldn't have had. The biggest thing, this is my personal feeling, not a lot of Americans necessarily share it, or half the Americans share it, half of them believe it's completely false. I think he was an incredibly courageous man. He did everything that he did, not for any personal gain, only because he said, this is wrong, this is not appropriate. The NSA now is able to tap into communications that the Constitution is not necessarily allowing them. Nobody knows about these things. The US public needs to. Right? But I think everything that he did was highly courageous. It was something like, I need the world to know, and not the world really, the US to know, the public to know that this is happening because this is not correct.
So that was the ethical element in his approach.
Yes. There is, large number of people in the US, particularly those associated with the military, call him treasonous. I actually think he was incredibly responsible even in how he gave out the information, because he gave it to reputable news sources and he told them, you filter this out. You make sure that nobody live is going to be compromised with this thing. Right? So he was very careful about this. But again, these are my opinions. Analyze them yourself.
He also said, that Amazon cloud is not secure. Then he said Google's interdata hops are not secure.
No, he said that was being tapped. Okay, so what Google was doing, generally Google security practices were very good. Okay? The problem is they assume that if they have either a fiber optic or lease line, I forget whether it was that or not, that they assume that could not be tapped. Right? And they say, boss, our lease line is connecting our two data centers. Why should we bother encrypting this stuff? Right? There is separate revelations. So this was one thing, right? So this made Google really upset. They said, boss, NSA is tapping into our data without our permission. Separately, he also revealed that Google was working with the government on certain accounts without telling people. Look, Google is a company. They operate in the US. They have to follow US laws. They have to follow the laws of any country that they operate in. Otherwise, they will get nailed. Right? So, Google had to, if you produce a certificate from FISA court or a US court which says you are required to cooperate with the NSA on this particular thing, they have to cooperate. And the answers, he said, they were cooperating, and maybe they were cooperating even more than them. Right? NSA might have early on paid them for certain things, and then they would have said, yeah, you can have access to that. Google was very upset that their lines were being tapped because that was being done without their knowledge.
They did it because they knew backdoor access to those.
No, Google did not know that. So after that, Google tightened them.
But for inter data center hops, is there a cost to it in terms of compute costs if you encrypt them?
It only symmetric encryption is dirt cheap. And now, early on in 2000, public key encryption was kind of slow. Now you can even do thousands in a second on a PC. Computing power has increased quite well. And optimizations have increased quite well. So you can do a lot more, but it's still more expensive than symmetric encryption. And either ways, the cost of that is not very low. In the overall scheme of things, costs are not very low. Okay, now we are completely in story time. So this is just around Pula. So firstly, I guess, I don't quite know how we are going to answer this question politely, right? Which parts of this are interesting, which are not? Should I cater in a particular direction? I don't know that we have that much time left anyways.
Tell us a little bit about Bitcoin and digital signatures.
Okay. So, digital signatures I kind of already talked about, right? I talked about digital certificates, I talked about digital signatures, I can technically sign any kind of documents, stuff like that. Bitcoins, and I had read about it in more detail sometime in the past, more recently I haven't. I have become a manager these days, so, and mildly forgetful. But what I will do is I will talk about the Bitcoin ledger mechanism. Actually, I'll talk about a couple of interesting points in Bitcoin, and I'll cover Merkle hash trees also in the process. And I'll show about how these basic elements are used to build more interesting elements. Okay? So let's start with this problem. I have some data ABC, I have some data DEF, I have some data M and O. Right? I have a bunch of data, right? And there could be a million items up here. I want to create a signature. One way is I can just sign this whole thing, create a hash, just sign it. That's a signature that this whole data exists. Oh, sorry. So I have data ABC, DEF, M and O.
Can you write it in black, possibly?
If you have black, there's a.
Blue is better.
I want people to be able to verify. Simplest solution. This is used. I take all the data, I hash it, and I sign that. That is my signature on something, and now I can ship that data along with the signature to anyone. They can verify. Correct? Okay. Suppose I want to be able to identify that a particular item existed in this, in this list. But I don't want to send that whole list across because the whole list is megabytes of data. Whereas an individual item is just 10 bytes or 20 bytes of data. How would I do something like that?
Give up.
Give up?
So during at the time of encryption only, make packs with the.
I could do packs, then I'm reducing the size, but then I'm also signing more times. So that's a little more painful. So here was a cool idea, and by the way, the guy who came up with this idea was somebody called Ralph Merkle, who's one of the two guys who co-invented public key cryptography. Okay, and he invented that when he was a good student somewhere or the other. What he said is, let me take this data, let me hash it. Let me hash this. Right, so hash ABC, hash DEF, hash MNO, hash QED. So on and so forth. Now I'm going to take these hashes and I'm going to combine them to create a new hash here. Combine these two, create a new hash here. You guys, whoever's writing code knows about trees. All the way at the base, I get one hash, I assign this, right? Now, when you want me to verify that something exists, you send me ABC, you send me that hash, you send me that hash, and you send me the signature. And you can recompute the whole thing. So you only sent me one data item, a few hashes, which is log to the base 2n, right? So not a lot of data, and the signature. This was called the Merkle hash tree. Okay? So this is one interesting problem. Now I'll talk about another interesting problem. Suppose I want to look for the absence of data. How would you want to do that? So this was a cute invention that somebody did at Valisa. What he did, and this the guy who did this invention for us was the guy who did the timing and the power analysis setup. What he did is he created ranges. So the first range is from minus infinity to ABC. The next range is from ABC to DEF. The next range is from DEF to MNO. The next range is from MNO to QED. So now what you're doing, and this is obviously sorted, right? So everything in the range is not in my list of elements, but anything that is, a trailing element is da 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 da. So this was kind of an invention that we got a patent for at Valisa. And there's another cute idea. Okay, so I talked about Merkle hash tree. Merkle hash trees for absence. Bitcoins actually uses this concept of Merkle hash trees to go create a list of transaction records. So you have a list of transactions, you're kind of creating a Merkle hash tree element, and you're creating this hash at the bottom to kind of say that these are all the transactions that have happened in this particular system. The other interesting thing was the guy invented a few different things, and again, whoever invented Bitcoin was another one of these gods, right? You don't argue with them at all. So, if you had posed this problem early on, is it possible to create trust in the absence of any central authority or trust in any central authority? The answer before that would have pretty much been, right? Because even with that whole digital certificate world, you had to trust VeriSign, right? There was a key that you built into your product. Without any kind of trust mechanism, what this guy did is he built this blockchain thing, and then he created, effectively said that now there are a set of people who are going to try to solve a mathematically hard problem. What is the mathematically hard problem? The mathematically hard problem was, so you have this hash over here, right? So call this hash head, hash x. Find me a number so that the hash or the hash add, this doesn't work, dude.
Okay, use the
There is no black, right?
So you use the red.
Okay. Hash of hx plus some number results in something that has the last, say, 10 bits as 0. Now the deal is, I kind of gave you properties of hashing functions, which is it is hard to create hash functions that map to. So now the thing is, the miners, the Bitcoin miners, are guys who are going through a set of different numbers to say what combined with this is going to result in a hash value that contains enough zeros. And the interesting thing is, now I can make this problem harder and harder by first saying only 10 bits need to be 0, 11 bits need to be 0, 12 bits need to be 0. Every time that I increase it by 1, you have to go through 2 times as many numbers. And there is a race between you and other people. Right? So, again, this is why you call this guy a god. Not only did he create a very cool problem that a lot of people could try and solve that was hard to solve, he allowed this problem to be made harder and harder over time. Right? So, this is, I don't know if any of you guys have read the Foundation trilogy, but this is kind of like the second Foundation acting, controlling a system that is going out and making stuff happen in the future. But this was, I thought, an absolutely amazingly brilliantly designed system. And he provided incentives for lots of people to want to do mining by saying that if you figure out the answer, then you will get a certain amount of money. So you're giving incentive now to millions and millions of people to actually go to mining. Right? Now, we can have a separate discussion which should not be part of this session around whether Bitcoin will be successful or not, but that's a different discussion.
So is there one originator you can attribute to?
Yes, there is one originator. There is one god.
Is that god name?
He has a pseudonym.
Is there a
Satoshi.
So it is a pseudonym.
It is a pseudonym.
He can't be found anywhere on the planet.
He cannot be found anywhere on the planet, and he is worth billions of dollars if he chooses to sell his Bitcoin. Because initially
he has started.
He started it. He was the only person mining it. He was trying to get other people to mine it. Nobody was willing to mine it. He was kind of posting this in groups which were worried about libertarianisms, right? Who kind of don't want any centralized control. There were a set of people who wanted to work on that stuff. And he was trying to push people to go do it, and nobody was interested. You could use a PC and you could generate lots of Bitcoins.
So how has he kept his own identity quiet?
He essentially stopped sending mails, he stopped participating, he doesn't do anything with it.
When he starts selling his Bitcoins, even then he will remain...
He will remain anonymous because somebody who has a particular key owns a Bitcoin. Right?
By very
That's
nature
what
of the system, he will remain anonymous.
Sorry?
By very nature of the Bitcoin system.
So the Bitcoin system allows you to track the money that a particular key holder holds. But I can always generate new keys as long as I know how to manage them. So I can become multiple people on the Bitcoin system. Now you could try and use my IP address to start figuring out. So you could get to more and more levels of sophistication. It becomes a cat and mouse game.
Some of the exchanges, I think Mt. Gox closed down. Shut down.
So Bitcoin has gone through ups, it's gone through downs, it's gone through ups again. It's kind of in a semi-flat stage. It's not at bad news, it's not at great news. I believe you might still be able to buy a Tesla with Bitcoin.
Yeah, and they do have Bitcoin ATMs too.
Yeah, and you can actually look up on the net what the current value of Bitcoins is. I don't know what it is. Might be $746 as when I last looked, which was some time ago and I haven't bothered. But as I said, different discussion. But yes. Generally do not take bets that I don't know how to bet. So yes, he's a good one.
Wasn't he a Caltech graduate?
I mean, you can speculate all you want to, and if he was a Caltech graduate, that would reduce the number of people in the world very dramatically. I don't know that anyone can accept that. And with a name like Satoshi, we believe he's of Japanese descent, and that might be true and that might not be true. And when in his life did he figure out that he wanted to use a pseudonym and not be associated with this thing? I have no clue. Right? There is all great speculation and not too many facts. So, all right. Cool. Late in the evening, guys. Thank you for being so patient.
You missed the iPhone.
Yes, we can. Sure.
Government OS.
But I'm letting various people. So the interesting thing around the iPhone. Okay, so now I guess whoever wants to go can go. Maybe we stop recording it.
Now you'll have to stop recording it. That's the important.
No, that's fine. That's fine. I've already said various things that one assumes that there's enough of a prelude to the talk that nobody bother with the rest are not important enough that it's okay. So the FBI request to address, to unlock the iPhone and what were all the different issues involved, right? So I think the FBI originally was also quite capable of unlocking the iPhone or getting people to unlock the iPhone. They found this to be a great case to be able to say we can require the phone manufacturer in this particular case to build stuff so that we can ask them to unlock anything. I don't know that they completely expected Apple, because Apple I think in the past has cooperated with them. I don't know if they expected Apple to take as strong a stance or what happened and how this whole thing became public. Once it became public, then it became a political battle, right? Where Apple effectively took a stance that we cannot unlock this phone without writing new software. Okay, so here's the thing, right? What FBI said is, this guy's a terrorist, he's done terrible things, completely inexcusable, all public opinion is behind us. You must help us unlock this phone. And we want to publicly demand that you help us unlock this phone. And you can only help us unlock this one phone, you don't have to help us unlock anything else. What Apple said is, once I write this software, and what they say is don't necessarily help us unlock the phone because maybe you don't know what the passcode is, but even after, provide a new version of your OS so that even after 1 million attempts of wrong passwords or 1 billion attempts of wrong passwords, you don't wipe out the phone because that's what the current software does. First thing, and secondly, don't start delaying me after I try the first 10 attempts. These were the two requirements. So they said write us a version of that software that can do this. We will use it only for this one phone, and then we won't use it again.
But there's something I don't understand. To get the new software into the phone,
Apple has the ability to unlock. No, so Apple has the ability to do updates.
Right? To install the update, there is a manual intervention required.
Apparently not. Apparently not, right? Apple has a way of kind of forcing some security stuff.
Apple can remotely do that.
Yeah.
so that they were ready to do. That bit, not write the new software, to force the new update on you.
No, that already existed. If it didn't exist, they couldn't build it in, right? Because then you have to unlock the phone to get to anywhere. So the answer is that capability already exists.
And does BlackBerry also have another
Dude, I think BlackBerry lies through its teeth. So at this stage, I don't know what to believe. And frankly, if you're using a BlackBerry, are you serious? Thank you. I wouldn't necessarily. There are other people I know who still use BlackBerry as their primary email phone, including Deepa Kamli, who's a classmate of mine. So, okay. So the deal is that Apple. So FBI said, boss, build this software. Worst case, you can lock it to only this device. So that OS will verify the device ID of this device, and then only run. So that it will only run on this device, won't run anywhere else. Apple's counter argument to that was, boss, today you're telling me to do this. Tomorrow you will give me another 100 devices and say you've already written that software, tie it to this other device. Now unlock this other device for me. You will be forced to unlock it. Not only that, the Chinese government will come and say you are selling in China. Here is the device, please unlock it. Now, following Chinese laws, if somebody is a dissident, somebody is making critical errors. First Amendment, I haven't written the software as yet, I don't have to provide it. Right? Even if the government orders me to, I can say that software does not exist, I can't give it. As soon as the software exists the first time, then that excuse disappears. Right? So that was the whole battle around this.
Finally, they got someone else to do it.
They got someone else, which they could have done up front, but they thought this was a great case to try it on so that they could get Apple to create that software for them. Next time it would have been much easier. Cool.
Okay, thank you, Ambarish.
Thank you.
My pleasure. Thank you, guys.
So all this app